Brian. Brian, he's one of our own. He did his BS and Master's at University of Illinois. He's an excellent student. I had him in a couple of classes, and he's now doing his PhD with Professor Butler, and he will be discussing the RAS and GRAB in asphalt concrete from a modeling point of view and experimental point of view. So I will turn it to Brian. Brian.
Can you hear me all right? Yes. Okay. Thanks, Professor Al-Kadi, for the introduction. You can probably tell from my voice that I'm a little bit under the weather today, so I'm going to keep this fairly brief. I don't want to lose my voice halfway into the middle of it, but thanks for coming out. For my opening slide, you can see that one of the sponsors for the project is the National Science Foundation. So it's a goalie study with an industry partner, and our industry partner is Road Science LLC. So quick shout out to them. A little bit of a loaded title, RAP RAS asphalt mixtures. We did a little bit of testing with Southwind RAS on some field mixtures in the Chicagoland area in Bartlett. So I'll talk a little bit about some of the experimental testing results with that in kind of a first section. And the second section, it's more of looking at the difference between a virgin and a RAP mixture using discrete element modeling with some digital image correlation added in. So I realized that some of the work that we do at ICT with Professor Al-Kadi's group, they delve a lot more into RAP RAS testing and looking at modulus and push-pull testing, all that stuff. But I'm going to focus more on just some quick field testing that we did of 3 mixtures, and they're all N30 base mixtures with generally high RAS contents, specifically the N30 FM96 and N30 FM98, and I'll describe those in a minute. The traditional N30 that they use in District 1 and what they used on this project, I'll just call it N30 Reg. That's what they call it up there. That mix had 3% RAS in it, and it was the FM98 product. And between FM96 and 98, the only difference is that the FM96 has tabs in it. So the tabs are generally a little bit stiffer, and the question was whether or not they could use that and whether the virgin and the recycled asphalt would mix very well, whether they'd have any issues with it. So they wanted to try it out there in their mix yards, so then they could just monitor performance over time with it. You can see the virgin asphalt percentages in the ABRs. So it was around 40% for the N30 regular. The N30 FM96 and the 98 were very close in terms of ABRs. The other thing I want to mention is that the volumetric properties in terms of the VMAs were kept pretty close. We wanted to check that. We didn't want them to be too far off, otherwise it'd be a little bit difficult comparing them. And then the final thing I want to point out is that the N30 regular mixture had PG5828 in it, and the other 2 mixes had 4634. So we kind of wanted to see how that would affect things in terms of Hamburg wheel tracking tests. That should be should have been able to tell us whether or not we had issues with binder mixing, whether we'd have permanent deformation problems, and then obviously the suite of tests that we generally run in our group with DCT tests and IDT strength and creek compliance. And then we added in ILITC modeling. I'm not going to show ILITC results here, but I'll discuss that towards the end of this section. Not sure if this is very hard to see or not, but you can see that the N30 FM96 mix had probably the biggest issue in terms of rutting resistance. We think that that's mainly due to the mixing between the tab recycled binder. That was a big issue for them. Trying to mix those. The other thing that they had problems with, and I can pass the sample around, but they had issues with RAS clumping at times, which I think is a major consideration that we need to deal with when we start to add in RAS to our mixes. And then they also have RCA in this mix. So if everybody wants to take a look at that, you can. So again, the N30 regular was a PG5828, but this is a 4634. So you can see that when adding in the recycled materials and increasing the ABR, and ended up that the N30 regular and the N30 FM98 were fairly similar, but the 96 really had some issues in terms of permanent deformation. The good thing was that we saw that helped us a little bit in terms of the DCT fracture energies. Now, I do want to point out that at the 10,000 pass level, they all passed the maximum rut depth requirements for IDOT, so that it met all the standards. The only problem was that it just wasn't performing as well as the 98. But it did perform better in terms of the CMOD fracture energies with the DCT test in -12. We tested both cores, which the core is being passed around, but we also tested lab compacted samples. Didn't see any statistical difference between those two when we remixed them. But all these mixes also passed the minimum fracture energy for low criticality projects based on the low temperature cracking study that was done at University of Minnesota. That project finished up, I believe, 2 years ago, and it was a pooled fund study between Minnesota, Illinois, Wisconsin, and a couple other states. But their recommendation for like a base course mix was a fracture energy of 350 joules per meter squared or more at tested at a temperature of the PG low grade +10. So we based our PG low grade on the environmental climate, not the low grade of the asphalt binder itself, or I guess the virgin grade of the asphalt binder. In terms of the peak loads, you can see that the FM96 had the lowest peak load in terms of the DCT results and slowly increased. So you can see that there was an effect of using a PG4634 as composed of a PG5828. And that held the same ranking looking at IDT strengths as well. The IDT strength of the FM96 was lower than the 98 and the N30 regular mix, and this is at -10. The reason why we tested IDT strength was just to have it as an input for the ILLI-TC model. ILLI-TC requires creek compliance, IDT strength. You can get strength from the DCT peak loads, but we found that with recycled materials, trying to take the correlation that we originally had for some of the mixtures that we have in Illinois, if you correlate DCT peak load to IDT strength, that doesn't remain the same when you start to add in the recycled materials. That changes a little bit, so you have to be careful about that. And then in terms of the creek compliance, these are fitted creek compliance results with a power law model. You can see that it's a little bit funky in terms of the N30 FM96 mix. Initially, generally you have a pretty asymptotic creek compliance initially, up until maybe around 10 seconds. And this is a fitted creek compliance master curve with the reference temperature -20. We didn't really see that with high ABR mixtures, and we've seen that quite a bit with high RAP mixes as well. That using a fitted power law model, you really have some issues, or not some issues, but it looks a little bit different in terms of the fitted creek compliance at lower temperatures initially in the creep test. The other thing that you can notice is that the N30 regular mixture seemed to perform just a little bit better up until about 10 seconds, but beyond that, the creek compliance of the N30 FM98 and the 96 were better, which generally would tell us that, as we have a higher ABR, but if we adjust our virgin binder grades, it seems like we're offsetting it a little bit in terms of the overall stress that we'd probably develop in terms of a thermal event, so we can get away with binder grade bumping, which is obviously something that we're happy with. You just got to be careful with the Hamburg results, making sure that we don't have too much permanent deformation. And then in terms of the ILLI-TC results, the reason why I didn't show those is because we didn't find any issues with any prediction of thermal cracking. We didn't have any situations where we actually even reached a thermal event that would cause the crack to initiate, which was a good sign for these mixes. And we used the Chicago climate and this input information. I forgot to mention, but Hermione Wang is sitting over there. She did quite a bit of that work as well. So that being said, we're monitoring these mixtures. This is just an early peek at the lab testing that we did last year or this past year. But we're going out to their facility and taking a look and seeing what goes on, hopefully this spring, to see what happened over the winter with some of the thermal cracking that might have occurred there. Kind of the more interesting stuff for me is using discrete element modeling with digital image correlation testing of DCT samples. There's been a lot of work with discrete element modeling, whether it be here or other universities. And I'm going to focus on low temperatures, so I know that there's been a lot of work looking at prediction of modulus and other properties, whether it be a heterogeneous simulation or a homogeneous discrete element model simulation. But I'm going to focus only on low temperatures. So the work that was originally done at the University of Illinois with dealing with low temperature fracture of asphalt concrete was done by Hyunwook Kim in Professor Butler's group in 2008. And the whole idea there was just trying to match load displacement behavior and then trying to do something with that information from a normal stiffness, shear stiffness, and just trying to relate those back to what they actually means from more of a micromechanics level to the global scale. There's a little bit of a problem there with just trying to understand it because it didn't make a lot of sense at some points. What we thought was we could try and go through and not only calibrate it and adjust it using the load CMOD behavior, but we can also use this digital image correlation. I talked, I believe, last year about digital image correlation a little bit. I know that some other people in the room probably do a little bit with digital image correlation. I'll describe that in a later slide, but we think this is a promising way of using discrete element modeling just so that you're not only looking at trying to match a global load CMOD behavior, because that's really just giving you a small input of what's going on in terms of the material response. In terms of the DCT test, just to quickly go over this, I know I showed some DCT results earlier, but developed in our research group, so we kind of got to plug it a little bit. But displacement control test, obviously applying load in the vertical direction at the loading hole such that we can propagate a crack horizontally, evaluating the fracture energy as load under the curve normalized by the fractured area. And this has been traditionally the only thing that we grab from the DCT test. Sometimes we might try to put a camera here and check how the crack propagates or how fast it propagates. But if we don't use advanced methods like digital image correlation, I think we're missing quite a bit of the information that we can possibly glean. So in terms of the current DEM approach, or I guess the DEM approach that was done previously was you go ahead and you run uniaxial modulus tests on the mastic phase. Then using IDT strength information, fracture energy information, whether that be from an SCB or from a DCT, you can go through and evaluate input properties, specifically for a case where you're assuming that it's linear elastic. That was the assumption originally. We're still doing some elastic simulations. We also do viscoelastic simulations with the discrete element modeling as well. But then the whole idea is trying to get the modulus Poisson's ratio so that you can get these stiffness properties for the stiffness model, but also inputting contact models between the mastic itself, the mastic and the aggregate as an interface, and then the aggregate. And that work initially was done again by Hyunwook Kim and Mike Wagner. In terms of the contact models, the aggregate is a little bit of a different animal. Obviously, the aggregate we would just assume has no softening, so it just reaches a peak strength and then fractures. The mastic and the interface are a little bit different from the aggregate. Then we always assumed that the ratio between the strength and the maximum displacement, and I should say that this is traction on the left-hand side or the vertical axis and displacement on the horizontal axis. But for virgin asphalt mixtures, we always assume that this stayed the same, the ratios between these two strengths and these two displacements. based on the work that Hyunwook had done. So we kind of went through and backed that out with a couple different mixtures that we did this last year. That being said, we generally would assume that, again, the interface is going to have a lesser strength and a lesser maximum displacement. And we've seen that with some of the testing that Salman Akimzad has done on interfaces between asphalt and aggregate, asphalt and asphalt layers. In terms of the image processing procedures, I think that was the biggest step that we had to deal with the discrete element modeling of heterogeneous simulations. Originally what was done was using a scanner and then going through and using a proprietary image processing method or a software that would basically spit out the heterogeneous sample. We didn't want to do that anymore. We wanted to go through and just simply take an image, and that being a pretty high resolution image, 21 megapixels, but trying to take an image of a specimen and then being able to use freeware to evaluate, or I guess set up the DEM geometry. So what I would do in this case, because I was using digital image correlation as well and I had to apply a speckle pattern, before I applied the speckle pattern, I'd originally taken an image of the specimen. So if we zoom in on that specimen, you can see the aggregate, the mastic phases. So then using some image processing techniques, which have been outlined in work that Aaron Kanan and some other people have done at Michigan State or Wisconsin, we can easily create a binary image considering asphalt and mastic, and we can adjust what we consider mastic based on a maximum aggregate size. And then you can easily, using MATLAB or some other type of software that you want, you can evaluate the outlines of the aggregate. You can evaluate whether a specific DEM particle is within the mastic phase or the aggregate phase, or whether you're considering that contact to be an interface. And I do want to point out before I go any further that we did only use particle flow code. I know that there are other discrete element modeling softwares out there. I know that Professor Tutumler's group uses different discrete element modeling softwares, but we focused on PFC 2D. We're trying to eventually go to PFC 3D, but that will be something in the future. So once we get the output image, we're able to take and create a text file, and that text file can be read in the PFC program, and then it can easily output the geometry, whether it be a mastic, an aggregate. In this case, I made it origin blue. So in terms of the digital image correlation method, I'm not going to really get into the crux of it like I did last year, just because I think a lot of people have seen digital image correlation now. I could talk about it further if you want in the question and answer, but right now we're focusing on using CCD cameras, Stingray, F201C, just so that we can have higher speed image procurement. We do have a 21 megapixel camera that we use at times, but that's mainly for creep compliance, just because the amount of the size of the displacement field, or the magnitude at least, is much smaller in terms of the creep test. So we need to be more resolute in that case, but it's just too slow for us to be able to use it in a fracture test. We generally use a full field method with DIC as compared to other CAN softwares that you can get, whether it be VIC 2D or VIC 3D or some of the other ones. And we focus on using that prior to crack propagation, just because it seems to provide a little bit more of a continuous field. So using cubic B-splines, and again, I can get into that if anyone has any questions. In terms of the configuration that we use, it's not perfect, and this is with the HREL configuration that we have. With the new DCT machine that we have on campus, we're able to have cameras on both sides of the specimen instead of just one side. So that makes it a little bit nicer. But with the method that we use at HREL and what was used for this testing setup, we have a DCT specimen. We make sure that it was approximately perpendicular to the CCD camera. So we go through a geometry check first. And then we had LED lights both inside and outside This image, I screwed it up a little bit, but these LED lights are actually outside of the chamber. One thing that we noticed a lot was that if you put LED lights inside of the chamber, you have a lot of issues with moisture that starts to get on the surface of the LED lights, and then trying to go through and evaluate whether it's actually a deformation change, or whether it's a deformation or whether it's actually a lighting issue. In some of the images was extremely difficult. So we started to bring the LED lights outside of the chamber, and then in terms of testing, I would go through and put the specimen in, put the initial seating load on the specimen, check that the camera is positioned properly, and then I'd wait 30 to 45 minutes just to make sure that the temperature was maintained as constant as possible, and then that would avoid any issues with moisture droplets on the window of the chamber as well. And that's something where actually with our configuration on campus, we have removable windows. So now we don't have to have any glass covering where we have to deal with some of the reflections and stuff like that in the camera from the glass. Because the one issue that we have is with the CCD camera testing at -12. That's about the lowest temperature that you can take that CCD camera to, and if you get any moisture inside that camera, then you're pretty in trouble. So in terms of applying it with discontinuous behavior, we have found that trying to use a normal DIC method with discontinuous behavior is just really not applicable. It's okay if it's fairly continuous and there's just a small discontinuity, but when you start to have a large crack, then you have some problems. So this reference might be a little bit small, but we use the subset splitting method right now as a method of getting around that with DIC, and there's a lot of specialized DIC forms out there to date, but this is the method that we've found is probably the quickest at getting fairly accurate results. In terms of the pre- and post-processing operations, essentially we gather in all raw images using LabVIEW programming. So LabVIEW is really set up to use CCD cameras with a FireWire cable. So we simply gather in the raw images. We try not to ever use JPEGs just because the compression that you have in a JPEG can be really problematic with some of the applications that we have. Our camera is I think it's a 4 megapixel. So if you start to really compress that up, you can have some issues with some of the accuracy. In terms of pre-processing, we convert everything to TIFF files. The TIFF files do not do any compression, and then we also remove rigid body rotations. The way that we test DCTs, if we load it vertically, then in the Instron, if you ever watch it, I mean, it will rotate quite a bit back and forth during the test. We don't have that issue as much with our new setup, but we have to go through and remove rigid body motion and then remove our region of interest, or ROI, in the pre-processing stage. And then from that, we can process our source and target images. We do that either in MATLAB, or we also can use add-ons in ImageJ, which is pretty quick. And then we go through in MATLAB and post-process, and then we can easily retrieve the data and analyze it from there. So in terms of the mixtures that I tested and then evaluated using DIC and DEM, it was just a 45% wrap mix. This is an old slide, but just getting into some of the green engineering principles, but it's just based on some of the testing that I originally did in my master's thesis with evaluating warm mix asphalt mixtures and wrap. We did the normal mechanical performance test that we have up here at HL. We also did some acoustic emission testing, but the biggest thing we found was that although you might see an improvement in terms of the Cree compliance and the bulk viscoelastic material response with having a warm mix asphalt and even adding in some wrap to it, when you really start to add in wrap up to a level of maybe 45%, you see a distinct drop in terms of the DCT fracture energies, irregardless of whether it's a hot mix or a warm mix. So the warm mix isn't going to help you too much in terms of the crack propagation. So if we focus on a virgin and a 45% wrap hot mix, you can see that from a load CMOD standpoint, it's pretty definitive that, with a 45% wrap mix, we're seeing higher peak loads, but in terms of its softening curve, it's pretty steep, and we've seen this quite a bit with different other recycled components being in our asphalt mixture, so I'm not going to really get into that too much. In terms of what we did for the heterogeneous simulations with discrete element models, specifically with PFC 2D, it can be problematic trying to add in viscoelastic material response with a contact model that we have. So in this case, I'm just going to show some of the elastic simulation results just because we haven't published the viscoelastic stuff yet. But I assumed the instantaneous relaxation modulus at -12 from IDT creep test. So whatever it was, whatever that E0 value is, that's what I assumed for this mix. So instead of just going through and just approximately figuring out whatever KN and KS were from other people's research, we did pull that value out from there, and then we backed out what our parameters were for the mastic and the aggregate phases. In terms of the DIC results, this is just kind of what we generally produce in terms of what it looks like just from a load CMOD stance, so that the green box is just showing where during the test the image was taken. The result on the left-hand side is all strain in the vertical direction, and it's microstrain. Keep that in mind. And the crack is or the notch tip is actually right here at about, I think it was 35 millimeters, and at 0 in the X direction. So you can see that strain localization is definitely something that we see as we start to increase and go towards the peak load. But you can also see that it's interesting when you start running the test, you don't see too much. Well, you see a little bit of straining up here, but the loading holes are right around here, and then all of a sudden, as you start to get towards the peak load, you start to see a contribution to the strain field from the loading holes, and not just localization at the notch tip. And then we actually started to see the crack propagate immediately prior to the peak load. So at this point, with around 1,000 microstrain, we are starting to see some pretty significant damage. And this is the 45% wrap case. With some of the wrap mixes I've tested, I've seen quite a bit of the time that we actually see the cracks start to propagate just a little bit before the peak load at -12. So with that being said, once we hit the peak load, we are seeing some pretty significant cracking already happening through the specimen. I would say probably up to around 17 millimeters. And then this just shows the approximate crack path through the specimen. Now, what I will say is that this is a zoomed out version with DIC. I wouldn't ever go through and try to do too much prediction with digital image correlation with a camera that we have at 60 millimeters and 50 millimeters, so 50 by 60. That's really zoomed out, but I just wanted to show that in this case. Generally what we do is about 15 to 20 by 15 to 20. It's pretty small. It's much smaller than this. In terms of calibrating the DEM of the DIC, I'm not going to really get into those details because I'm starting to lose my voice already. But in terms of the deformation zone lengths, this is one thing that we looked at was deformation zone lengths, but we also looked at adjusting based on kind of a box grid where we looked at specific discrete locations throughout the DIC field, and then we tried to estimate those and adjust in the DEM accordingly. So you can see in this case, at this specific time, we found deformation zone lengths that were pretty similar between the DEM result and an elastic simulation. And I think we're doing a better job with the viscoelastic simulation now that we're adding that in. And then in terms of the elastic simulations with both virgin and 45% wrap hot mix asphalt, you can see that, and this is just one example with the 45% wrap mix, this image over here, but You can see that we matched the load CMOD pretty well with an elastic simulation. But you can see that the major issue or the major difference was in the separation in the contact model. The forces that we had, or the maximum forces in the mastic and the interface, really didn't change too much. But when we started to add in the wrap material, that's where we started to see a big drop in terms of the maximum separations or the local fracture energies in the mastic and the interface. And one thing we're working on now is trying to be able to do a better job estimating the interfacial properties, because going through and estimating those is really difficult. With the mastic, it's easy to go through and run fracture tests. With the interface, it's a little bit more of a challenge because you're trying to make a large specimen out of mastic on top of an aggregate, and you're wondering whether or not that's actually really applicable to what's going on here from a micromechanics standpoint. And then these general remarks are just based on the second section of this presentation, but just showing that heterogeneous analysis, even if it is an elastic simulation, which can be done pretty fast, we can do it in about 2 hours, it does a pretty good job going through and matching with a bilinear CZM in discrete element modeling. We were able to match the zone lengths with DIC and DEM pretty well with some pretty quick calibration methods. And then it's just showing further evidence that binder grade adjustments, not only from an experimental standpoint, but also from a modeling standpoint, it seems like it's giving further evidence that we might need to think about doing that, and it's a good idea to do that at times. So with that being said, before my voice is completely gone, thanks for your attention. If anyone has any questions, fire away.
Questions for Brian? All right. Go ahead.
I am curious about the, like you were saying, about how to get data from that interface, how small of a scale you have to get down to properly represent that. You can't do it on the size machines we have.
Actually, I'm going to try it out this summer. I'm going to talk to you about that.
Perfect.
No, because that's something that, to be honest, is one thing that with Hyunwook Kim's work, people just always questioned it. And we're wondering, can we run some of those tests? There are some pull-off tests that people have done at like University of Nebraska-Lincoln, but they do all their discrete element modeling mainly at higher temperatures. So when they run it at 25C, maybe those pull-off tests are a little bit better, but when we start to get down to -12, those pull-off tests really are just, measuring a strength, and you're not going to get any displacement. So is that really applicable in this case? And again, with the way that the aggregate is located, in some points you're going to see compression instead of tension. So is that really, and sliding? So, do you need to run, like an Arkin type test that has shear and normal components to it? So yeah, it's a good question, but that's something that research has to vet out. Yeah, some people are looking at that too.
All right, Brian, thank you so much.
Azir just asked online, for slide number 12, which thresholding technique did you use to generate a binary image?
Slide number 12.
That's what he has.
I think it meant 13. What threshold?
Which thresholding technique did you use to generate a binary image?
I mean, it's watershed transformation. So, I mean, Mazir, I can talk to you about it later and give you a reference. I mean, I basically went through and adjusted based on the recommendations from Aaron's work that had been done at the University of Wisconsin. So I based it on that, and some of the verbiage I can't remember the exact names, but we adjusted based on that, and we also adjusted based on what aggregate we wanted to consider to be part of the mastic phase, because that changes.
Thanks, Brian.
Professor Barenberg has a
I'm
question.
sorry.
In one of your slides,
Mhm.
a few on down, you showed your cut that you made in there. You knocked that up. You show your cut going into a large size aggregate.
Yes.
Your sample is about 2 inches thick. What is the biggest aggregate you use?
I don't like using really large aggregate mixes in fracture tests because I don't think that it's a good idea. But I try to stick to 9.5 millimeter nominal max aggregate size mixtures. So I think, what is that, like the 12.5 is the top size for these samples. But I have seen that, at times we'll test mixes that have 25 millimeters, so an inch, and yeah, that really creates some issues with some of the COVs that you would get.
Yeah, I would think that the bond then between the aggregate and the strength of the aggregate would become a big issue.
Yeah.
And it results in the initiation of that crack.
Yeah, and I think that's been seen not only with DCT tests, but also SCB work that was done by a lot of people in this room as well, and Cosmin, who did a lot of work with high RAP mixes with base courses. So yeah, it's a definite concern when you start to have large aggregates.